All right, so let's talk briefly about these trebuchet projects. And unfortunately, I wish more people were here, but I want to make sure that we get this out. We haven't had a chance to do it yet. So first of all, construction. You guys all did a good job. As far as I know, I need to double check the rubric, but as far as I know, everybody got their full 50 points. A couple of you got some extra. There was one group that broke some rules as far as height restrictions, but because of creativity, that made up for it. So I think everything has been a wash there. So good job on that. So the big thing now is the papers. All right. So again, the format of the paper is that it should look like one of your lab reports. All right. So again, you want to dig out those lab reports from first semester. Look at the comments that I made. Again, each person needs to do their own work. So format, cover page, pretty straightforward. Background. For this one, I guess, so I usually the background, I usually think of it as either an explanation of the concept being explored, like we did the one about the modified Atwood machine, right, with the pulleys pulling the carts, right? Isn't that what we did? Yeah. The last big lab report was where we had the carts with the pulleys and the, right? And so that was about Newton's laws. So not when your background should have been about, you know, Newton's laws and acceleration, that kind of stuff. For this one, because the project is build a trebuchet, you probably want to just say a couple sentences about the background of like what a trebuchet is. Okay? So historically, what was their purpose? How do they work? Okay? Make sure that the reader knows what a trebuchet is. Okay? That should be your background. Purpose, what are you trying to do? Shoot a marshmallow as far as you can. Right? That was it. Hypothesis, I don't know what I would do for that, to be honest. You know, hypothesis, we think we'll be able to launch a marshmallow more than 50 centimeters. Cool, all right? So don't stress over that. These are each, I think, just 2 points anyway. Materials, pretty straightforward. You guys, the materials is not a paragraph. It really ought to be a bulleted list, okay? Cool? Cool? All right,
Will we have to, like, sort of, as part of, like, the procedure, will we have to include the construction of the construction?
Yeah. Yeah, that's largely what the procedure is. Okay? All right, so yeah, so procedure. So it says right here, this is where you'll discuss how you constructed the trebuchet and how measurements were made. Okay? And this is like the bulk of your grade is this part. Okay? So I'm going to be looking for either drawings or photographs with labels. Here's how we measured the length of our lever arm. Here's how we measured the height of our counterbalance. Here's how we measured this. Describe to me how you found masses. Did you build your full lever arm and then drop the whole thing on a scale? I don't think most of you did that. Most of you measured one popsicle stick and multiplied it by the number of popsicle sticks and said that's how heavy my lever arm is, right? Okay, so you need to describe how all of those measurements were made. Okay, here is a list of the measurements that you should have made. The mass of your counterweight, the mass of your throwing arm, the mass of your projectile, any important dimensions. So there's a list there. All right, my thinking is you'll probably include a couple drawings. You'll probably have one drawing that looks like I'm going to make sure that assistance is not needed. No. I don't know if you need help. Okay. No, please, sorry, you're fine. Okay. All right, so here's your marshmallow, here's your counterbalance. So I would see you making two drawings. One in the pre-fire state, right? And you're going to say, oh, we measured the height of the counterbalance and the starting height of the marshmallow, right? All that kind of stuff. We measured the length of our lever arm. I'll talk about this in a minute, but you know, maybe you call this, I don't know, L1, you call this L2, whatever. Okay, so that's going to be one of your drawings, right? All right, you'll probably want another one that illustrates what's happening at the moment of fire. Right? The idea is your counterweight's going to come down and your marshmallow is going to go up. Right? So now you're going to have two more heights, right? Does that all make sense? Andrew, you good? Everybody good? All right. So show me how you make all of those measurements. All right. Initial angle of your throwing arm. That you can probably just measure with a protractor, or you can use some simple trig to find that angle. I'll talk about that in a minute when we get to torque. All right. So those are measurements you're going to make of the construction. Then you did some test launches. All right. And basically there, the things you need to give me some values for are how far the projectile travels in the air. Okay, like from being projected until it hits the ground, not including rolling, okay? And the time that it's in the air. All right, the time that it's in the air is going to be quick, right? Yeah. All right, so there's a couple ways you can get that. You can try to measure it with a stopwatch. If you want, you can calculate it. You might be able to find a way to calculate it by making some other measurements. Okay, so go back and use those projectiles equations. Or another option is, you guys all have smartphones that have a slow-mo video capture option, right? So the other option is fire it a few times and record it in slow-mo. I believe, and you can check your settings, but I believe that you can figure out what frames per second is, and I think it's whatever the time is on the display. I think for most phones, if you multiply it by 8. That gives you the actual time. Or divide it by 8, rather. Divide it by 8. Okay. Because I think it's like 30 frames a second to 240 or something like that. So those are some options. Does that make sense? Okay. Now, if you go the stopwatch route, that's fine, but that's going to be a source of error, right? And it's something that you'll need to talk about. Follow? Okay. And then down here it says, calculating this information does require several or more runs of your trebuchet before the due date. Be aware there are two important parts to the trebuchet's operation. The motion of the counterweight, and then the projectile part. Please make sure you distinguish between those two parts of the operation. Follow? You could almost even break it up into two separate chunks, you know? All right, everybody good? Questions? I'm getting a lot of blank stares. Is everybody good? Okay, cool. So remember, the goal behind the procedure is that the reader ought to be able to repeat your process and come up with comparable results. And so don't write it like, oh, hacker's going to know what I'm talking about. All right, remember, the rule is I ought to be able to give your paper to Mr. Pata, the physics teacher over at North, and he ought to be able to read it and know exactly what's going on with your project. Sorry? No. But I should be able to. Okay? Cool. So read through all this stuff. It's pretty straightforward. All right, graphs and data. You're not going to have graphs, probably. I don't know what you would graph. Okay? You're probably just even going to have very little data, right? You're going to have, whatever, maybe 5 trials and distances and times for each, or whatever. Okay? There's not a ton of data. Okay? That's what I just said. I don't think there are any graphs. If you want to be creative, great. But most of this is just copied and pasted from the general lab report rubric. But I think with this one, there aren't any. All right. So everybody good with that? All right. What's up, Abby? Good.
Where is this going to be?
What do you mean?
This recording?
Oh, I'll put it. I'll show you when we're done. Okay. So everybody good up to here? Okay, calculations. So my recommendation is at the back of your lab report, you're going to have a section that says calculations. And you'll have calculation number 1, rotational inertia of counterweight. Calculation number 2, rotational inertia of throwing arm. And then in your papers, you refer to those values, you can put, see, calculation number 1. Does that make sense? Like a bibliography? Okay? Like an index, exactly. Follow? Okay, so let me say that again. Your calculations, you're going to have a section of your lab report that says calculations. And then you'll have them numbered. Calculation number 1 will be this. Calculation number 2 will be this. Calculation number 3 will be this. You probably will have other calculations besides these, but these are like bare bones minimum. Okay? Then, as you're writing your paper, you might say, you know, we calculated that the rotational inertia of our throwing arm was blah, 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 blah. And then in parentheses, you put C calculation 1. Follow? Okay?
Now, what would be the best way to put the calculations in? Because it's hard, it's kind of a pain to type them all, like...
Ideal situation would be to use an equation editor, and next year I'm going to require that 100%, but this year, because things have been a little rocky, if you need to handwrite it, that is fine.
Alright.
Follow?
Can we handwrite them?
I don't understand why handwriting. Oh, I see. It's just so that it doesn't look like.
Yeah, it's like mine later.
If you handwrite them, then you need to handwrite your own. Okay. I don't want to see two people printing in the same handwritten calculations. Okay. Okay. So how do you do these calculations? I want to kind of run through these. All right. So the problem is, how do we calculate the rotational inertia of something complicated like this one? All right. And I know not all of your trebuchets look like this, but you all had some sort of lever arm and some sort of counterbalance and a marshmallow, right? So how do we calculate the rotational inertia of this? All right, so here was the main thing I wanted to talk about. So here's what you're going to do. Easy peasy. So here's your thing. Here's your lever arm. Here's your counterbalance. Here's your marshmallow. Cool? So the problem is, if you look at the rotational inertia sheet that I gave you guys at the beginning of the year, there's, not at the beginning of the year, but you know what I mean. There's one that is a thin rod rotated about the center of length L, and it tells you that I for this thing is 1/12 mL squared. Okay, but the problem is, for most of you, your pivot point isn't at the exact center, right? Yeah, it's some ratio of the way around it. So there's a way we can deal with that. You can use what's called the parallel axis theorem. Those of you who take AP next year will learn that. We're going to do it a different way. All right? The other way to do it is this. On that same sheet, there's another equation for one where it's pivoted around the end, where this is L. Okay, and for that, I is 1/3 mL squared. Follow? You guys need to hear this. You've never seen this before, so those of you in back need to be following along, please. Patty and John. All right, so is everybody good with that? All right, so what you're going to do is this. Here's your trebuchet. You're going to treat it as two rods. The green rod has a length of L1 and a mass of M1. And the blue rod has a length of L2 and a mass of M2. So you'll need to do a little approximating about that mass, right? Maybe you got to do a ratio or, you know, whatever. You know, like this is 2.6 popsicle sticks or whatever. You know what I mean? Okay? So let me finish my train of thought and then I'll get questions. All right? So then what I can do is I can calculate the rotational inertia of this end. I can calculate the rotational inertia of this end. Cool. You also need to deal with the rotational inertia of the battery. All right? So the idea is the battery is traveling around in a circle, but it's at a pretty big radius, right? So for the batteries, you can just do the mass of the batteries times, on my drawing, it would be L2 squared. Does that make sense? Why I'm using L2? So anybody confused about that? All right. And then similarly, your marshmallow is going to be somewhere. So the rotational inertia of the marshmallow would be the mass of the marshmallow times whatever, some radius squared. Cool? So there are 4 rotating things. There's end 1 of the arm and 2 of the arm marshmallow counterweight. So calculate each of those individual rotational inertias, and then you literally just add them up. In the same way that you could add total mass, you can add total inertia, rotational inertia. Follow? All right, so that'll give you the rotational inertia of this whole structure. Does that make sense or no?
Yes.
Zach and then Christine, sorry.
No, you answered.
Did I? Okay, that's what I was hoping. Yeah.
Isn't a brass that's containing less than a battery intensity?
Totally. Yeah. And again, because this is a first year course, we're going to make some oversimplifications.
Okay.
Yeah, you're right. Because I mean, even the fact that this is rotating complicates things. So it is what it is, and we're going to, do the best we can. Okay. Yeah.
I think that did you mention if we rotate a sling as opposed to a basket?
Gotcha. Yeah. So if you have a sling instead of a basket, again, you're going to have to make some oversimplifications. Because your radius is always changing, right? So I don't care how you approach that as long as you give me a good explanation of why you did it the way you did.
We just take the sling off and put a basket.
No, I don't think I want you to modify what I saw you fire. So it's fine. I mean, it's not going to make your calculations any harder. Honestly, probably the easiest way to deal with it would be to find the radius when it's at its closest point, find the radius at firing point and maybe take an average, you know what I mean? Just something like that. I don't want you to overcomplicate things. If you're not sure, take an average, okay? All right. Yeah, Max.
So what is the radius? Would that just be L1?
In this case, yes. With a sling, no. That was why I used R here, specifically because if you had a sling, it might be something different. Good, you guys? All right. So I think that right there is the only calculation that we haven't done, where we've had to add rotational inertias. Okay. Everything else that you should have to do in this report is calculation you've done before. Good. Any questions? Are we feeling okay? Not too overwhelmed? Yes? That's where I'm headed. Okay, so everybody good? All right, so, okay, so calculations for the trebuchet measurements. You need to find the rotational inertia of the counterweight. Talked about that. Rotational inertia of the throwing arm. That's the green and the blue added. Total rotational inertia of the trebuchet. That just means those four things added together. Cool. All right. Notice I didn't, when I wrote this, I apparently was in a different frame of mind. I didn't write anything about the rotational inertia of the marshmallow. Why? Yeah, the mass is so small compared to everything else that rotational inertia is going to come out to be basically zero. So it might be that you calculate that rotational inertia and you add it in and it doesn't make a difference. That's fine. Just tell me that. You know what I mean? Yeah.
So if we're omitting calculations like friction, where do we build that?
That'll be in our experimental sources of error. Good. And or you could also include that in your calculations. You could say, to simplify, we've assumed friction is negligible. You know what I mean? Something like that. All right. All right. Initial torque provided by counterweight. So on my drawing here, here's my counterweight, right? So somebody name for me the force that's providing the torque. Gravity, right? Point for me. Which way does gravity point? Straight down, right? So this is going to be the mass of the counterweight times the acceleration of gravity, right? That's my force of gravity, right? So we'll call that mg for a minute, right? Well, remember, you guys, torque is RF sine theta, right? RF sine theta. So on my drawing here, what's my R?
L2.
L2, right? Because this is my pivot point, right? So that's going to be L2 times F is this force of gravity times the sine of theta. Now, I remember you guys struggled a little bit with this on this test. What's theta? Good. It's the angle between the force and the lever arm. It's not how far the thing rotates, it's this. So you can measure that with a protractor, or you can do some simple trig, or however you want to do it. And I don't care what you do, just explain it. Yes, and then yes.
When you calculate does adding a weight to the end of that half of the throwing arm, does that change whether or not the center mass of the throwing arm itself provides torque as well? Does it not?
Say that. Oh, I gotcha. Oh, I gotcha. The in most cases, the mass of the counterbalance is so much bigger than the mass of the arm that the torque provided by the center of gravity of the throwing arm itself is going to be negligible. And you could, I mean, if you wanted to say something about that, awesome. Yeah.
If you have a hanging counterweight, the fade is always going to change.
That's going to be true for all of them because the angle of the lever arm is always changing. So, and that's why, did you guys just hear what Josh just said? Your angle's always going to be changing, right? So notice the way I worded this on the sheet. It doesn't say find the torque, it says find the initial torque. In other words, I'm saying, I know the torque's going to change, but at least show me that you understand how to calculate torque. Follow? Pretty good. I'm surprised a few of you are writing this stuff down. All right, initial angular acceleration. All right, well, what produces angular acceleration, you guys? Torque. So, torque equals I alpha. We just figured out the torque. We just figured out I. Find your alpha. Cool? All right. All of this stuff is conservation of energy. Okay? Once you've done your conservation of energy stuff, you'll know your RKE and you can find your angular velocity. Okay? So this will be, using this guy will be RKE equals 1/2 I omega squared, right? So you can find your omega. And then once you know your omega, you can use a jumper to find your velocity, V equals omega r, which you can then use to find your kinetic energy of the marshmallow. Cool? No, that's wrong. I lied. Sorry. Rewind. You need your total energy to stay constant. So you can use that to find your kinetic energy. I guess there's all right. I'm realizing now there's a couple ways you can do this. So, I'm going to say something that's going to frustrate a couple of you. There are 3 or 4 ways that I can think of just off the top of my head to do this chunk. As long as you use some appropriate way of finding those values, I'm happy. Okay? This here says use the kinetic energy to find the velocity of the projectile. There are other ways to find that velocity. So as long as you use some valid method to find the velocity of the projectile when it launches and explain how you did it, I'm happy. Cool? Okay. Cool. All right. And then projectiles measurements. Once you know that, you'll know your initial projectile or your velocity. And then you can do calculations to figure out the height using the projectile's equations. Yes?
So with this thing that the launching velocity, we should just treat the arm as if it was solid again, not with or does it not matter? Because it doesn't matter, right?
Oh, for the sling thing, you mean?
Yeah, if you use concentration energy.
Yeah, correct, yeah. But if you take another route, you need to make some simplifications, I'm okay with that. Just, let me know when you do. Good, you guys? All right. Honestly, you guys, I think the calculations part of this is going to be the most time-consuming. So my recommendation is, if you've not started this, try to tackle that over the weekend. So if you've got questions, you can ask me ahead of time. You know what I mean? So you're not like sitting at home Wednesday night going, I don't know how to do this because I can't help you Wednesday night. You know what I mean? So try to do some of that over the weekend / between now and Friday and see what you can get done. All right? Yes.
Do you want them to be colored? Does it
I don't. If you have color, cool. If not, yeah. All right. Cool. Sources of error. Friction. We ignored friction. We timed stuff with a stopwatch that is too quick for us to accurately measure given human reaction time. There's air resistance on the marshmallow. We oversimplified the sling motion because the motion was too difficult to, whatever. Cool? There's a ton of sources of error here. Give me, 3 or 4 of them. All right? Conclusion. Tell me how you did. How do the principles of physics apply? What issues did you have that you tweaked? You know, like, oh, at the beginning, our trebuchet just fired the marshmallow straight to the ground. But then we added in a little stopper thing that made it go flying. We tweaked the angle of the finger thing. Whatever. You know, analyze your results. Maybe you found out that your trebuchet gained energy. Give me some reasons why that might have happened. Okay? So your conclusion is analyze your results and tell me what happened. Cool? Ordinarily, your conclusion should be a response to your hypothesis, which for you guys is, I bet we can make this thing go 50 centimeters.
We did.
We did, but then tell me some more, you know? All right.
Yeah,
If you have time to do that and would like to do that, that would be the coolest thing in the entire universe. And I would give you the biggest high five the universe has ever seen.
If you did what?
If you came up with some sort of alternate experiment, such as modifying your counterbalance, the mass of your counterweight, and seeing how that affects the range. Awesome, that would be badass, and that would give you some graphs and stuff. And to be honest, when we first sat down to do this, that was one of the things we talked about, but we knew we were head on top. Good, you guys? Awesome. Any questions? All right. Does this feel manageable?
Would you go for like energy conversions?
Can I go over the energy conversions? Yeah, I mean, so the idea is in the initial state, basically all of your energy is gravitational potential energy, right? So I would say, all right, well, there's going to be gravitational potential energy of your counterbalance, right? So that's just, you know, MAGH, right? Presumably, for most of you, what's the starting gravitational potential energy of the marshmallow? 0, right? So that means that my total energy before I release this thing is going to be, let's call this X. It's going to be X, right?
So what if it wasn't 0?
Would then add it in.
It would be added or would it be subtracted?
Oh, I see what you're saying. It would still be added in. Is that right?
And actually, the height of the trench is added to your counterbalance.
Say that again.
Like, if, for example, if you had wheels on the trebuchet, 50 centimeters would be added.
I gotcha. Yeah, that's going to raise both of these things up. So yes, that's fine. Yes, because then all that's going to happen is the kinetic energy, or the gravitational potential energy of your marshmallow, instead of going from 0 to some big number, is going to go from slightly bigger than 0 to some other slightly bigger number. You know what I mean? So I think that still jives. Because you're going to lose GPE over here and gain GPE over here. So that's, yes, that is legit. Yes.
Is the angular acceleration of the counterweight is the same as the firing it, right? So if you found that acceleration, you could use that to find the velocity.
Yep, the whole arm should always have the same angular values at any given instant. Okay, so that's your first calculation. Are we good with that? All right, then at your moment of firing, now the GPE of your counterbalance is 0-ish, or close to 0, right? The GPE of your marshmallow is, we'll say, M. But now there's some kinetic energy and rotational kinetic energy, right? So find the rotational kinetic energy of your system such that your total energy is still X, right? So this ought to then just basically be, you know, basically X minus M, right? And so now you can find your angular velocity. Does that make sense?
The angular velocity.
What happened to the kinetic energy?
The kinetic energy of the marshmallow?
Yeah.
you could add that in for sure. I think it's going to be pretty insignificant because that mask is so small. Yeah, so I guess, yeah, technically that would be another variable in there.
If we don't use it, we can just say that the mass is marked.
Exactly. Christine, you good? All right, so that is that. Again, I wouldn't wait too much longer if you haven't started. I know some of you guys have. Some people have already been coming in and asking me questions and stuff, so good. Yeah, I mean, we're sort of up against a wall here time-wise, so, you know what I mean? So, as much as I'd like to say, I don't think we can. Plus, I think Mr. Hernandez would punch me. It will be, yes.
Yeah, I think that's.
All right, everybody good? Questions? Okay. There you go.